This is a demo to introduce you to the ARIES for PeopleEA Explorer, which is a web-based application built on the KLab integrated modeling platform. The application has access to all information available on the integrated modeling network and provides dedicated user interface to allow the pilot countries to easily access and test the output of the PeopleEA project, funded by the European Space Agency and developed by the ARIES team at BC3 in collaboration with the beta team and using the OpenEO platforms. Over this tutorial, we're going to see how to access the ARIES for PeopleEA via a web browser. We'll have an overview of the accounts currently available in the application and how accounts can be compiled on the selected context. So we're also going to see how to set the context in the application, and then we'll run the account on the forest condition index, show the results and explain how this account was built. Then we're going to provide another example of how ecosystem services can be run, and in the last part of this tutorial we're going to show how to export the results. Let's get into it.
To access integrated-modeling.org, you will need an account. Click on the Sign Up button and create a username with your email. And register. You'll receive a confirmation email. Once you've received your email, you'll have a password and you'll be able to log in with your username. And you can access the application ARIES for PeopleEA.
Let's have an overview of the accounts. The panel on the left of the screen shows the accounts currently available in the application. Please note that the project and the scientific information available evolves. New accounts may be added, and the current accounts may be based on different models and data. The accounts available covers extent, condition, and service accounts following the SEEA structure. The first option is to compile the forest condition index to estimate the overall condition based on a set of experts defined, weighted, and selected indicator. At this stage of the project, condition accounts are focused on forest ecosystems due to the ecosystem relevance in terms of ecological conditions and the availability of information from remote sensing data. There are 3 indexes available. The forest condition index developed in the PeopleEA project. A second option to compute the same PeopleEA index but weighting the condition indicator using the Euclidean distance, and the forest condition replicating the original methodology that was published in 2023 in Network Communication 14, article number 3723. The next session shows the PeopleEA condition metrics. You can notice how in this section you can observe each individual forest condition variable, so the raw values coming from remote sensing data that are used in the current compilation of the accounts, as well as the forest condition indicators. The difference between these 2 accounts is that the first observe the original data, while the second is rescaled based on reference values. The next section shows the PeopleEA high resolution variables. These variables are placed in another section to differentiate them from the other raw variables. Caution is required when observing these datasets. High resolution observation should only be observed over a small context. You can take as reference the location designed as testing areas in the project. For example, the level 3 of the nomenclature of territorial units for statistics, or NUTS 3. This request is due to the computational cost and time associated with these observations, which when using the dataset is much higher and longer. So this first section shows the options to compute accounts that record the condition of ecosystems in terms of selected characteristics at specific point in time. Over time, they record the changes to their condition and provide valuable information on the health of ecosystems. Another important aspect to notice is that before triggering the computation of one of these accounts, you can already know which is the main output that is expected from that option. So in this case, you can see that this output is a table. For this condition index, instead is a map. And this information is available for all the other outputs as well. In the last section, we have also an example of ecosystem service accounts. In this case, we have the sediment regulation or the soil erosion control accounts, and the possibility to compute this account using the OpenEO cover management data. We'll see this in an example later on. The last section shows the ARIES for SEEA accounting table, which are also available in this application. This follows the same structure of the SEEA framework and provides extent accounts both for ecosystem type as well as land account, condition accounts with different forest condition metrics and different type of outputs, and ecosystem service accounts both in physical and monetary terms. In the last part, there is also spatial and temporal aggregation settings, in which you can decide if you want the accounts to be computed only on the first and last years that you will be setting in the context, or if the output should be summarized showing all the years in the time series. As previously mentioned, to trigger the computation of an output in a specific area for a specific period, the user should first select the context. To do so, the first section of the panel on the left of the application provides the option to do so. Now, the geographic area can be selected by using the map boundaries, which in this case would set the context as the overall area observed in my screen. You also have the option to select administrative region, which select the greater administrative entities in the area that is observed currently in the map. And by zooming in and out, this reacts and change the context of your analysis. You will also see how the spatial resolution adjusts when I change the location on the map. The last option is to use context by river basin, which define the area based on the FAO hydrological basin information. In this context, administrative region are the preferred option to select accounts, since they respect political boundaries, which are usually the one used for this kind of application. A third option would be to select the context from the spacebar, in which you can indicate the geographic location by typing in the name that you're looking for with the capital letter. And in this case, also the system provide the option for a geographic location that you can select, and the system set that as the context of your analysis. The geographic scale, so the spatial resolution, also play an important role, and the user can select different options. You can choose between meters and kilometers and directly type in the resolution that you want to use. This can also be locked, so that this will never react to changes in the map. As you can see, in this case, the resolution stay consistent with the 2 kilometers set. The user should also define temporal boundaries of the analysis. A single year analysis can be triggered. In this case, the box in this section is unchecked, and you just indicate the year of interest. To show change over a longer period of time, check the box and select the first and last year of the period to analyze. So for example, 2020, 2018. Once you have selected the context of your analysis and you trigger the observation of one of the output available in the application, in case you did a mistake and you want to change the context selected, you can simply press to interrupt the computation and reset the context. Let's now see an example of how to set a context and run an account. To do so, we can select the Veneto region in Italy, and we select the years to be observed to be 2020. And then you trigger the computation of the sediment regulation, soil erosion and control, but first we run the OpenEO cover management data. And once this observation is complete, I can then call the sediment regulation soil erosion control. And this model will be computed based on the information that I previously observed. So on the cover management from the OpenEO platform. As you can see, whenever the ball starts spinning, the system computes the model and provide the inputs that are needed to provide the result to the query asked by the user. Once the model is complete, the results are summarized in a table. Please notice how in this case, results are categorized by forest type and the bioregion in which this forest type is located. If we go back to the view data section, all the input used in the analysis can be observed individually. And here we have the map of the retained soil mass from vegetation in ton per hectares, which is the spatial explicit information that was summarized in this table. The reason why I first called on the observation of this dataset before querying this model is to show that observations are live digital twins. Any observation done in ARIES happens on the fly and is not a predefined combination or workflows of models and data. The system builds the most appropriate strategy to answer such question using the information available in the system at the moment in which a query is made. For this reason, as new information is integrated into ARIES, its results improve. So in this case, ARIES look for the best available combination of data and model to estimate soil retention. And by selecting the input of the C factor from OpenEO, the model used this dataset to compute the accounts. If I move to the view documentation, in the section in which the dataset use are shown, I can see how the annual Inca C factor raster is used for the raster calculation, and this dataset comes from OpenEO. This particular dataset has a high resolution both in spatial and temporal terms. And instead, you can notice how a clock here appears, meaning that for this particular observation over the period observed in our context, the system could find more temporal observations. Now, we're going to compare these results against another model that instead run using the ecosystem service accounts in physical terms in the ARIES for SEEA accounting tables. And to do so, we're going to reset our context. And I'm going to set again the same context, but this time I will run this using the sediment regulation, the soil erosion control from the ARIES for SEEA accounting tables. In this case, the system produced the results based on the information that is still available in the ARIES network, but the information from OpenEO won't be prioritized. So in this case, the results obtained are still estimating the soil erosion control physical supply, but first thing that you may notice is that the categorization is done by ecosystem type as defined by the SEEA framework, while previously we had this result categorized by forest type and by the European bioregion. And also another difference is that the same output is this time using a different cover management factor. So this doesn't come from OpenEO. This is a model that uses information from the land cover to provide an estimate of the cover management. So in this case, there were two main differences for the same query. We can notice how the C factor has changed, and in this case it's static. There is just one observation, since the underlying information that is being used to build this is the land cover, and for Corinne in 2020 there is only one observation that actually is the temporal mediation that picks the data in 2018 and use it to estimate the C factor in 2020. And also the categorization is done by the ecosystem type, for which you can notice that another model has been built on the fly and autonomously by the system, simply because we were asking to estimate this model by using a different methodology. So this is an example to show how the system works and how ARIES computes observations by using the most appropriate information that is available to answer a specific question. So this also allows me to introduce the fact that the system is built to allow maximum flexibility, and local knowledge can be integrated into the system to adjust or to simply compare results using a different methodology, but also to integrate this information to be the primary input in the results that you want to compute. So other datasets can be integrated and parameters can be fine-tuned, and partially or entirely new models can be added as part of the workflow. A legitimate question might be, why do we have to select the OpenEO dataset? Is this particular data is more appropriate to answer these specific questions? Indeed, the data has highest temporal and spatial resolution and cover the spatial area that we were observing. The problem is that this data is not publicly available and thus is not chosen to build the model. This is necessary to ensure that early adopters have access to the data, and this may be the case for other national statistical offices or other agencies sharing other sensitive data and information in ARIES. So we provide this option for the early adopters to be able to compile the accounts observing this ecosystem service. A legitimate question is why this dataset is not selected automatically. Well, this was done on purpose to avoid that everyone in the integrated modeling platform is able to access this information that comes from OpenEO, and at the moment is not shareable as a public information. Now, I'd like to show you another example on how to compute instead the forest condition index. So let's reset our context. And let's change region. This time I'm going to use a different option to select the geographical area to be observed. So I'm going to administrative region, and then I'm interested in observing the region around Pamplona. And I will do so between 2017 and 2020. And let's change region. This time I'm going to use a different option to select the geographical area to be observed. So I'm going to administrative region, and then I'm interested in observing the region around Pamplona. And I will do so between 2017 and 2020. Once the computation is completed for 1 year, you will see that the temporal bar here starts moving from left to the right. In the moment in which all years have been observed, the values are summarized in a table, since this is the main output from the this forest condition index model. When all years are computed, the results are summarized in the table. which has information for each forest type, for each bioregion in the geographical area analyzed. As you can see, the results are available both as tables but also as maps. And whenever you see the clock next to a particular observation, this means that this observation has been, in this case, computed multiple times over the period observed. So it's a multi-year observation. So in this case, what the system has done, for each of the indicator in the condition index, the system observed the row variable, identified the minimum and maximum values for each of the combination of forest type and biogeographic region, and rescaled the original information into an indicator, and then weighted all the information from the indicators into a unique overall forest condition index. As it can be found in the information that appears when I go over the forest condition index people with the cursor, these are the indicators that have been considered. So above ground biomass, forest connectivity, NDVI, net primary productivity, soil organic carbon, and threatened forest bird species richness. I will now trigger the first option, the forest condition index people in this region over this period. As you can see, in this case, I obtain as a first observation the biogeographic region and the forest type. So you can see that these are the forest type. This information again comes from Corinne and show the different forest types available in this area. And I also have biogeographic region type. In this case I have three. I have the Atlantic, the Alpine, and the Mediterranean type. How for each indicator that is considered in this index, so NDVI, soil organic carbon, threatened forest bird species diversity, AGB, NPP, and forest connectivity, I obtain the observation of the row variable, as well as the threshold that I used as reference to define minimum values, so the values of in which the forest is not in good condition, the max, which are the values in which the forest is considered in healthy conditions. The original value from the dataset is rescaled to fit into this indicator 1. This is true for the other indicators as well. The indicator for forest connectivity, this was obtained by observing forest connectivity original values and rescaling it between the max and the min. Are then used within each type of forest, within each biogeographic region, to define the threshold within each combination of these two that were used to categorize the different forests in this methodology. And while here we can also observe the original data of the forest connectivity. We will see how in the final results we will have information about conditions in each combination of the bioregion type and the type of forest. The main output for the model just observed is this table. But in case we want to also observe this table for any of the specific condition variables or the indicators that have been used to compile the forest condition index, one can also query them individually. So for example, we can have results for the forest condition variables, which will appear here. And the same can be done for the indicator. Since the underlying information to obtain these accounts has already been computed, to obtain the results for the condition index, you'll see that tables gets out quite quickly. All the steps that you need to do to obtain the three main outputs from the forest condition index. To instead look at the map, these are the values for the net difference water index, and these are the results for the indicator. Those were already computed before. In what we've done just now, the results have been just explicit and categorized into a table. Some type by geographic region. Tables and maps are not the only results that is available in the Explorer. Indeed, you also have a report that is automatically generated that explains the methodology used, as well as documentation of the data that has been used. As you've seen previously, each of the dataset involved in the computation then has information in this section, in which there are also links and reference to the original dataset. There's also the view data flow that is shown earlier, provides an overview of the combination of data models that have been used by the system to produce a specific output. Each observation that you see in the view data can also be downloaded independently by clicking this button, and you see that you have the possibility to download it as a raster or as an image. The same is true for the table. It can be downloaded here, copy and pasted in, for example, an Excel spreadsheet, or directly download them as an Excel file. And moreover, here there is a table with the key outputs. In this case, the main output was the PeopleEA forest condition index. Is available here, and this, if downloaded, provide the maps for each of the temporal interval in which this output was observed. And this is useful to be able to further analyze the results in any GIS system that you may use in your team. So this is how you can export the results. All the steps taken in the compilation of this result is extremely transparent and well documented. And moreover, the system is not tied to any particular methodology or the use of a particular data or model. So we invite all the early adopters to compare the results that they obtain using different methodology, or potentially compare those results with those that have already available in their offices. And any feedback is warmly welcomed. And in case you have any local knowledge that you'd like to integrate in the system, this is possible, and we invite the early adopters to suggest those kind of improvements to the model. Thank you very much for your attention.